Okay, so quiz this morning is to figure out what kinds of radiation exist out there in the universe, as many as you can, and figure out a way that you would detect individual types of radiation or separate them or determine what's what. So tell me a type of radiation.
X-ray.
X-ray, okay, a type of radiation. Tell me about it. What kind of radiation is it?
It is like a wavelength.
Okay, it's got a wavelength, but so do electrons.
Um,
Is it energy radiation or is it particle radiation? Does it have a mass to it or is it just pure energy? X-rays are pure energy. They are light. They are electromagnetic radiation, right? So X-rays are just a high energy form of light. They're electromagnetic waves and they are pure energy radiation, okay? Anybody have an idea how you might detect whether or not X-rays are present? What do they use in hospitals to detect?
They use a CAT scanning machine. They do a simple photographic type deal.
So it's just a piece of film. X-rays will actually expose film, even if you don't open the film. Like in old cameras, you had to put the film in the camera and then close the camera, and then the camera would open the film. It would unwind the film in the darkness of the camera so that it wouldn't expose it. An X-ray will just see right through the camera, will go right through the camera, won't see anything, but an X-ray will go right through the camera and expose the film inside the camera. That's how X-rays were discovered by our friend Becquerel up here. So you can use a piece of film that's sealed up in a dark container that light can't, normal visible light can't penetrate, and that can detect X-rays because when you open up that container, if it has been exposed, in other words, if it looks like light has hit it, even though it was in a dark place this whole time, then you know X-rays were hidden. You can also determine how many X-rays, because the brighter the light on that, when you develop that film, you'll get a photograph, and the brighter the light is on that photograph, the more X-rays hit it. Okay? So it's pretty simple. Use film, just like they do in the hospitals. There are other ways to do it as well. What other kinds of radiation do we have out there?
Microwave.
I'm sorry?
Microwave.
Okay, microwave radiation is technically radiation, but it's not dangerous radiation. It's also the same thing as X-rays. It's electromagnetic radiation. So it's not any different than X-rays, it's just a different energy level.
I'm guessing X-rays are the same thing as gamma rays.
X-rays and gamma rays are the same.
Beta radiation.
Beta. Beta radiation. Anybody know what beta radiation is? What's beta radiation? Let's look it up. Unless you know what it is.
Is it like the sun? Or no, it's
The sun gives off beta radiation, but it's not the only thing that gives off beta radiation. There are things in this room that give off beta radiation.
not the sun. Like lighting?
It's not light.
So.
Oh, like cell phones and stuff?
Nope. Cell phones do microwaves.
It says here it's a beta particle, sometimes called a beta ray. That's it's a
Tanning tubes?
That's also light, ultraviolet light. Go ahead. Blake?
electron emitted by radioactive decay of atomic nucleus.
So it's actually not a positron, it's actually a beta radiation is actually an electron. If you have a beta positive, then it's a positron. But a normal beta ray is an electron. Remember yesterday we talked about instability in the nucleus. And when you have instability in the nucleus, a couple of different things can happen. The nucleus can just rearrange itself. The protons and neutrons can just rearrange themselves. And if they do that, they'll let off some gamma radiation, kind of like an X-ray. But if they rearrange themselves in such a way that one of the neutrons doesn't want to be a neutron anymore because it's just not stable enough to be a neutron, it can actually decay and become a proton. And if it becomes a proton, it decays and it kicks out an electron. It creates an electron. So a neutron can become a proton and create an electron and a neutrino in the process.
So beta radiation
Beta radiation is an electron.
is an electron type of radiation?
It's just a high energy electron particle. It's an actual particle of mass that will get kicked out of the nucleus. It does not come from the electrons going around the atom. It comes from inside the nucleus. So the electron is actually created inside the nucleus. It's born there. And it's kicked out. It's created from pure energy. What really happens, as far as we know, is that the neutron decays to pure energy. And then the pure energy creates a proton, an electron, and a neutrino in its place. As far as we know, that is what occurs. That's as far as we can observe. So, we caught it. But I won't get any further than that. But, so beta radiation. What other kinds of radiation? We've got gamma radiation, beta radiation. Are there any other Greek letters? Alpha. There's alpha radiation. Anybody know what alpha radiation is? We talked about that one a lot. That's the one that we bombarded the nitrogen with to create oxygen. Remember in the movie yesterday? The alpha particle hit the nitrogen, and nitrogen gained a proton and became oxygen. So what is an alpha particle?
Did they say that was a neutron fired at the
No, the neutron was fired at the uranium.
Oh.
At the nitrogen, they fired an alpha particle, which had actually 4 nucleides in it. Not nucleides, it had 4, what do they call those? Nuclear particles. No. Nucleons, I think they call them. Anyway, it has a combination of 4 particles consisting of protons and neutrons. I'll give you a clue, there's 2 of them, 2 of each. So an alpha particle is, what atom would it be if it had 2 protons?
Neutron.
If it had 2 protons in it, what atom would it be?
It had 2 protons?
Yeah, which atom has 2 protons? Helium. So actually what an alpha particle is it's just a helium nucleus. It's just the nucleus, it doesn't have any electrons kicking around it. It's just a helium nucleus that's been kicked out of something. And that's not, and it's got high energy again, but it's a seriously massive particle. It's got 4 big old nucleons in it. 2 neutrons, 2 protons. So the helium nucleus is actually on its own, if it's a high energy, it's ejected from the nucleus of another atom, it is an actual particle radiation.
So helium is like radiation
No. If you kick 2 protons and 2 neutrons out of a nucleus, like radium does this all the time. Radium is this guy right down here. Where is radium? It's over here. That's right on here. Radium over here. Radium normally has 88 neutrons. It's one of the biggest things out there in nature. Okay? There's only 4 that are bigger than it. So radium is pretty big and it's pretty unstable. It's radioactive. And it's so radioactive, so unstable that every once in a while it just kicks out 2 protons and 2 neutrons out of its nucleus. When it does that, it's losing 2 protons and it becomes radon. Radon does this too. It also will kick out 2 protons and neutrons and become polonium. And polonium is also unstable. It will also kick out 2 neutrons and eventually become lead. So every time it does this, every time it kicks out an alpha particle, it becomes something else. But those alpha particles come out with 2 protons and 2 neutrons stick together, so they're like a little helium nucleus. They're not, once they're kicked out, they do become helium. But helium itself is not radiation. Only when it's kicked out of a nucleus at high energy. That's when it's radiation. So alpha particle radiation is two protons, 2 neutrons all stuck together in a group, kicked out of one of these radioactive elements out here because they're unstable. They don't like to have those extra particles in the nucleus. This is why radioactive elements are rare, because they eventually decay. They eventually kick out the things that are making them unstable and become stable. Radioactive elements, all these radioactive elements up here are pretty rare. Some of them much more rare than others. Some of them don't even exist in nature, they're so rare. They might have existed in nature a long, long time ago, but they were so unstable that they became extinct very quickly as they became more and more stable by letting out these particles. So how could we detect alpha particles or beta particles? Remember, the alpha particles are a helium nucleus kicked out at high energy. Beta particles are an electron kicked out at high energy. How can we detect those things?
Beta and alpha particles?
Yeah.
I was kind of saying, like, maybe from an atom accelerator.
Okay, we could. I suppose there's something we could do with that. Not exactly the simplest way to do it, because accelerators tend to be a little bit tricky and maybe expensive, but not necessarily, I guess. But I'm not sure exactly. I mean, you could do it. I can think of a couple of different ways to do it.
Like the way scientists were doing it in the video.
But when they were doing that, they were just trying to create new atoms and break apart atoms. They weren't trying to detect the radiation. Let's think about this. What characteristics does an electron have? What do we know about electrons? Because remember, the beta particle is an electron. What do we know about electrons?
Negative.
Negatively charged. Okay, that's good. What else do we know about electrons?
They're super tiny.
Super tiny, really small mass. What do we know about helium compared to electrons? What's different about the helium nucleus? What is the charge of the helium nucleus?
Positive?
Positive what? How many protons does it have?
Two.
2, so what? Positive 2, right? So it has twice as much charge and it's opposite charge. What do we know about the mass of the helium nucleus compared to the electron?
They're about the same?
Heck no!
Significantly bigger.
Yeah, it's like 10,000 times bigger. Okay?
Shit.
An electron is tiny mass. Helium has 2 protons, 2 neutrons. They're massive particles. Okay? They're way bigger in mass. So now you have this huge massive particle that has a positive 2 charge. You have this tiny little particle with a negative 1 charge. How are you going to determine which is which?
The effects of the electric field on the
Let's use something like an electric field. Let's imagine we're in a room like this and we make an electric field go this way, from left to right. And then we shoot some alpha particles, some beta radiation, and some alpha radiation out into this thing. What are the alpha particles going to do if the electric field's going that way?
surface.
Yeah, are they going to get pushed very far? Because what determines how far they're pushed or how hard they're pushed? Their mass. Bigger masses get pushed, less or more. In gravity, they get pushed more. In electric fields, they get pushed less, right? So in electric fields, it's like pushing a heavy car, right? Heavy cars are hard to push, lighter cars are easy to push. So if you have a heavy car coming out, the alpha particle, so it's going to get pushed this way, but not a lot compared to the electron. Now, which way is the electron going to go if the electric field's this way? The opposite direction. And how much is it going to get pushed compared to this thing? A lot. So you're going to have some particles that are going to go whoosh way this way, and some that are just going to go a little bit this way, and now you know which is which. And in fact, you can use You could use a magnetic field as well. If you had a magnetic field that was going up or down, you would get the same kind of effect with the electric charges. Okay? But you could put all three kinds of radiation. You could also put the electromagnetic radiation, the X-rays, the gamma rays, and microwaves, and push them out in this electric field or magnetic field, whatever it is. Which direction would they go? Is light affected by electric fields or magnetic fields? No. So it would just go straight through. So now you have a detector for all three. Use electric fields or magnetic fields. And just let this radiation go shooting through it in one direction. And one charge will go one way, the other charge will go the other way, and the stuff that's not charged will go straight through. And now you've separated those three types of radiation. All right, turn in your quizzes. Put your name on them, put the date on them. Turn in your quizzes. Those of you watching by video should send it in by email. Let's see, what do we learned all the types of radiation. Here they do the experiment. Here, right here, look at this. Magnetic field. They use a magnetic field instead of an electric field. You can do it either way. They have a radioactive source that's giving off three kinds of radiation. Notice that the alpha particle doesn't get pushed very much. The beta particle gets pushed a lot, and the gamma ray just goes straight through. Let's see here. Is there anything else we not to detectors? There's a lot of ways to detect radiation. Geiger tubes are one that they're detected. You've probably heard the term Geiger counter. But a Geiger counter is it's a multiplier tube. It creates a very big signal from a small signal. So you have some radiation that's coming into the tube here from the left. On that's the red line is the radiation. And inside the tube, you have a rarefied gas. In other words, a low pressure gas in there. And the low pressure gas gets ionized. And as it gets ionized, it creates a positive charge on a wire down the center of the tube and a negative charge on the outside of the tube. And then when it creates that ionization because of some radiation that's coming through, then that makes a little voltage tick on the thing, and then they put a little sound in there so it ticks, and you can hear the radiation. They call radiation that is dangerous ionizing radiation. So radiation that is dangerous to the body and to other things will ionize molecules and ionize atoms. In other words, it will rip electrons off. Okay, so that's what they call it ionizing radiation, and that's what it does inside of that Geiger-Muller tube, as they call it. There are other things called scintillators. I've actually got one here somewhere. Got a scintillating material. Here's one. Got two. They use these to detect radiation, and these can detect a wider range of radiations depending on the material. But what these are is these particular ones are plastics that are doped with a material that gets that fluoresces, just like these light bulbs fluoresce with energy. These light bulbs you have to put electricity through them to make them fluoresce or to make them glow. But these ones will glow with just any form of radiation, even low-level radiation. And this one, you can see it glow on both of them glow along this long axis. So as the radiation comes in this way, they glow this way. You can see the glowing. It's lighting up, and that's not just because of the color of this thing, it's actual glowing. And this one as well. This one is actually the material that they use inside of the accelerator at Fermi. They actually both these materials. They give you this ruler there, and they give you this piece here. Also, you may have also seen this if you're a hunter. They use the same kind of material. They wind it up into coils, and then they put it on the sight. It can either be on a rifle sight or a bow sight or other kinds of sights, so that you can pick it out even in low-level light conditions. You don't need to have batteries to run these things, because they will work off of even minimal radiation coming from things like the moon. It doesn't take a lot of radiation to make these things glow. So these are very good materials for detecting radiation at all kinds of levels. They can really start to glow at high radiation levels. And you can tell that it's actually radiation from the lights because, see here, now what happens as soon as I cover it up? Does it go dim? On the axis, it should. There we go. Can you see that? It goes dim. It's not much because the radiation, it doesn't take much to light these up. But you can see I'd say it diminishes by, and it looks like it's just shadow, but it's not shadow, it's actually blocking radiation. I'd say probably by about 50% it blocks it. And it's just, all it's doing is taking light radiation, just regular low-level visible light radiation, a little bit of ultraviolet, not much. But anyway, those are scintillator materials, another way that you can detect radiation. There are many, many other ways. One of my favorite things that I saw when I went out to Fermilabs, because Fermilabs has a huge accelerator where they create all these great particles and new radiations. One of the really interesting things that I saw was a huge detector that was just filled with millions of wires, tiny little wires all woven together in this intricate pattern. None of them ever touched each other. They were just going, they were stretched across this big tube of glass. And it was just cool looking. It was essentially some kind of a multiplier tube, but it was very cool. Lots of different ways to detect radiation. And if you go to places like, if you went out to CERN, which is the big accelerator, the Large Hadron Collider, they call it LHC, you can see things like this. This right here where did it go? You're getting really weird things, advertisements, because it's the Daily Mail. Here we go. So this right here is actually a huge radiation detector. This thing is probably 6 stories tall. You can see this guy right down here. This thing actually starts below him, about 20 feet below him, and it ends up way up here. So it's 6 stories tall-ish, 6 to 8 stories tall. And there's just layer upon layer upon layer upon layer of different detectors inside of this thing. They have 2 of these. One of them's called Alice, the other one's called Atlas, I think, or something like this. But these things, just each layer is a different type of detector. Some of them are photomultipliers, some of them are other kinds of energy multipliers, some of them are scintillators, some of them are Geiger-Müllers, some of them are all kinds of things. And each one of these layers gives a different view of the information coming out of the collisions that happen. So here is a picture of the Large Hadron Collider. They have Atlas here. They actually have 4 of these. They have Atlas, Alice, CMS, and LHGB. They're not all exactly the same as the one I just showed you, but they are similar things to that. Like here's another one that's, you can actually see the layers in this one a little bit better. So anyway, as you're looking at this thing, these particles are created down here in this small ring, and then they're sent out into this big ring that goes around like 17 miles, and they're going around in both directions. So you have these particles that are going around in both directions, and they're constantly colliding. But at these places, they observe what's going on when they're colliding, when they hit each other. They actually try to measure what's going on and see what they can learn. And the data looks very much like layers. So here is what the data looks like. This is one of the it's not my favorite representation of the data. Let's go to a 2-dimensional view of the data. LHC data. So a better representation of the data, I think, is, here's a good one. So this one really shows you the different layers. So towards the middle here, you have essentially all the hardware that creates is where the particles are colliding, and then each layer outward, wherever you see these blue and green and yellow little things, are particle tracks. They're essentially they're detecting what the particles are doing, where they're going. And you'll notice that some of these particle tracks don't even begin until they get out to here. Like over here, this blue one that's going over here doesn't even start till it gets out to here. that means that either that particle couldn't be detected by all these other detectors up here, or it wasn't even created until it hit this detector. Sometimes the detector itself creates the particle because there's maybe some energy coming out that was undetectable, or some other reaction that happened lower down that created some energy, and that energy created a particle at this point. And, in the middle is where the actual accelerator is. That's where the particles are going back and forth and colliding. Out here is where the detectors are in each layer. And there are several layers of detector, and each one of these things is a little piece of data. And this is from one collision. It gets kind of crazy, okay? Well, technically it's from, probably millions of collisions, but you can treat it as one collision with the computer. But the point being is the data is extremely complex, but all they're really doing is they're detecting particles. They're detecting particles, they're detecting energies, and they have lots of different ways to do it. Out here you see this event over here that's obviously got some kind of swirly DNA-looking, tube-looking thing to it, but it doesn't even start till it gets out here. And this one looks kind of like it, except it's going the other direction, 90 degrees to it. So some really strange things happen when you start looking at this level of things. All right, let's move on. We've got to finish up this chapter. I didn't put a homework assignment out, did I, for this? Forgot to do that yesterday. So protons, electrons, neutrons, we've already talked about that. Here, they're actually going to calculate how small and dense a nucleus is. So the approximate density, they calculate first the radius of it using the Bohr radius here for iron, and then you use the mass of the proton and the proton and the neutron to calculate the density. It's not a terribly difficult calculation. You did one in the last chapter. Now here is something I really do want to show you. It's called the table of the nuclides, or the chart of the nuclides. I need to have one of these in my classroom, but it's a huge chart. It's kind of hard to find room for it. If you put an actual usable one in here, it would take up one wall, just about. So here's a good one. I like this one. It's not big enough. Need a bigger one. There's a nice one. Except I want to see one that has times on it. That's a nice big one. Okay, let's do that one. So let's view this image. So this thing is the chart of the nuclides. Remember that we talked about how different atoms can have different isotopes. What's an isotope? In the video.
Multiple versions of the same thing.
Yeah. So each atom has a certain number of what in its nucleus? What does this number up here represent?
Protons.
Number of protons. The number of protons determines what the thing is, right? It determines what each element is. Determines its basic chemical characteristics, for example. But that's mostly because of the number of electrons that are out there, because of the number of protons. But the point is that this number of protons determines what the material is, but it can have different numbers of neutrons together with protons, right? And there are certain numbers of neutrons for a given number of protons that are stable. In other words, there are kind of these happy spots where the number of neutrons and the number of protons balances each other really well. Because remember, the neutrons provide the force for holding the protons together. They provide that glue that we talked about, that gluon energy that creates the binding force that holds the protons together. A very difficult thing to do because protons do not like to be close to each other. However, if you don't have enough of those neutrons, there won't be enough binding force to hold the protons together. And actually, if you have too many neutrons, you don't have enough binding. The binding force gets unstable. It's kind of a weird way to talk about it. But there's kind of a sweet spot, just the right number of neutrons to hold those protons together. These black squares up here represent all of those configurations that are stable. On the x-axis, you have the number of neutrons, I believe. Yes, number of neutrons on your x-axis. On your y-axis, you have number of protons. So we start down here with hydrogen. Hydrogen, helium, lithium, right? So hydrogen down here, there are two very stable versions of hydrogen. One that just has a proton, and one that has a proton and a neutron. Okay? It's called hydrogen and deuterium. They're fairly stable, those two black ones down there. Then there's one that's kind of stable but not really stable. It's got two neutrons and a proton. It's called tritium. It's a little bit radioactive. It glows, for example. That's the stuff they put on divers' watches. Okay? So you have a little bit stable, but not really stable. It is a little bit radioactive. And then you have a bunch of them out here, where you add a bunch of neutrons, these orange ones and this purple one. You add one neutron every time you go to a square to the right. They're very unstable. So let's look at that a little closer here. You can see. So hydrogen has 1, 2, 3, 4, 5, 6, 7 known isotopes. Okay? But only 2 that are stable and 1 that's just relatively stable. Over here you can see the half-life of these, 10 to the 15 years. Okay? Or 10 to the 15 seconds, actually. So 10 to the 15 seconds. Hydrogen is going to be around for a very long time. It's very stable. Okay? Half-life meaning it takes that amount of time for half of the material to become to decay into something else. So if you're in that black region, right here, you're stable. You're not really going to go in there. However, if you get over into the yellows and the oranges and everything else, you're much less stable. The oranges are almost there. I mean, 10 to the minus 15 seconds, that's a femtosecond. These orange ones you can only make and then they disappear immediately. Okay? You look up here at aluminum. Where's aluminum? Aluminum is, which number here? 13. So it's the 13th one. We go up to Z equals 8, 9, 10, 11, 12, 13. So here's aluminum. How many stable isotopes does aluminum have? Huh? 1. Right? Aluminum is aluminum is aluminum. It only has 1 stable isotope. And that we learned in the video yesterday. And they talked about the different isotopes. They said that aluminum has only 1. But there are other isotopes. Aluminum only has 1 stable isotope. All the rest of them are extremely unstable. Right?
Hi.
Hello.
Could we get some classroom shots?
Sure, we're
Is
not
that
doing anything
okay?
exciting, like I said.
That's okay.
But anyway, aluminum has the 1 stable isotope, but lots of other isotopes. Those other isotopes are all things that are created in experiments. So you've got some that are in the blue region that have, like an hour, couple hours, few hours, maybe a few days even, half-life. They're going to go away quickly. But then everything else is pretty unstable. It's just going to decay and become something else. And as you go further and further up this table, you'll notice you have more and more isotopes available to you. So this big, I like to call this the banana slug of physics, right? It looks like a big banana slug. You know what a banana slug is? We have these in California, and the first time I taught nuclear science, we were teaching them I was teaching at UC Santa Cruz, and they have them everywhere there, and so we called it the banana slug. This is a banana slug. So now you know, and these things can be like this long. I kid you not. 2 feet long is not uncommon. Yeah, they can be pretty gross, and they're usually mottled. And the banana slug is also the mascot of the UC Santa Cruz sports there. But anyway, that's why I call it the banana slug, is because the chart of the nuclides looks like a banana slug.
Jared, are you going to need any photos for promotional brochures, or do you want to stage anything while we're here? This is what
Something
Ann will use.
photographically,
I don't think so right now.
Not right now?
Yeah.
Okay. Sounds good.
Thanks.
All right.
Yeah.
We're good?
Yep.
Thank you so much.
Yep. So anyway, so it's got this kind of peak. It's got these kind of points at the end, and that's because at the beginning you have very few isotopes because of the small size of the atoms. At the end you have very few isotopes because they're so extremely unstable. The stuff up there, look at the top there. The stability is terrible at the top. All those include the stuff that's out here at the the end of the periodic table, 118. It goes all the way up to 122 now, I think. But essentially, they make these atoms inside of accelerators and laser traps and other things. But as soon as they're making it, it's decayed and gone. I mean, they have such short lifespan. So uranium being number 92, right up here. Here's uranium 92, heaviest naturally occurring element. Has a whole bunch of isotopes, as do many of these things kind of at the top end of the middle of the table. Have lots of isotopes because they have lots of protons and they're pretty stable. If you have a lot of protons and you're pretty stable, you can add some more neutrons or take away some neutrons, and you can still stay pretty stable making a nuclide. But this table is useful in a lot of ways. One thing that's very useful about it is it can tell you what's going to happen to a particular isotope when it decays. So, for example, if you're uranium, one of the things that you can do right here is you can go through alpha decay, which means you can lose 2 protons and 2 neutrons. If you lose 2 protons, you go to the left. No, sorry, you go down 2. So you go down 2 from uranium down to what's 2 below uranium? Can't remember. So we go from uranium down to the thorium. Right? So you can go if you go down 2 to thorium, but you're also going to lose 2 neutrons. So you have to go to the left 2, so you know where you're at. And so you can use this table to determine what's going on with decays. And here they show this. Here's the atom that you start with. To go to alpha decay, you go down 2, and to the left 2. That's alpha decay. Beta minus decay, which is where it kicks out an electron, will kick you up to the left diagonally 1 spot. And beta positive decay, which is positron decay, will kick you down to the right. If you have a single proton decay, you go down 1. If you have a 2 proton decay, you go down 2. So different kinds of things that can lead you to different types of different places on the table of nuclides. So that's the same table, it's just arranged in a different way. We've got a few more things to cover here. So here they actually show some of these decays. They go from uranium-238 to thorium-234, so they go over 2 and down 2. And then thorium-234 actually decays through alpha or beta decay and goes to palladium and then back to uranium. So it goes from uranium-238 to thorium-234 to palladium-234, then to uranium-234. So one of its neutrons turns into a proton twice here and it goes back to uranium. That's kind of weird. It goes from uranium back to uranium. But then it alpha decays to thorium again, alpha decays to radium again, alpha decays to radon, alpha decays to polonium, alpha decays to lead. But it doesn't have to alpha decay to lead. Sometimes it alpha decays to lead, but sometimes it beta decays to astatine, and then to radon again, and then back to polonium, and then back to lead again. So there are different paths that different particles can take. There are some paths or some decays have a higher probability than others. So some things are very likely to happen, some things are less likely to happen. And this is the study of nuclear science. Nuclear scientists study the way that atoms decay through these different decay paths. That's really all they study, actually. When you're doing this nuclear study, the molecule the atom that is going to do the decaying, that is unstable and is going to decay, is called the parent, and afterwards it's the leftover atom is called the daughter, and you have then the decay. You have the daughter and the radiation. So you can represent this using the chemistry format. start with uranium-238. We put the little number up here on the left side of the number, and it's a superscript. That tells you the overall mass number of the atomic mass number, so the sum of the neutrons and protons. And then you show what it becomes, thorium-234, or it could become uranium. It becomes thorium-234, 92, and then 4 helium, and then thorium becomes uranium again, and so on and so forth. But so this 4 helium is, of course, the alpha particle. And now we learn how to calculate the mass defect. Okay, so when you go through these decays, there's always some kind of mass defect. That means that the mass of the stuff on one side of the equation is different than the mass of the stuff on the other side of the equation. Usually, when you're going through natural decays, the mass on the right is less than the mass on the left, and so you have this mass that turns into energy and releases that energy. But in man-made situations or in experiments where you're putting energy into a system, you can actually have more mass on the right than you have on the left. And you can create a situation where the reaction requires energy to be put into it for it to happen. But that mass defect, you use E equals mc squared to calculate the energy. The mass defect is the difference in the masses times c squared, the speed of light squared, equals that energy defect. So here they're going to calculate that energy emitted in the alpha decay of 239 plutonium. So plutonium, the 239 plutonium becomes uranium and an alpha particle, and the mass difference, we take the mass of plutonium and we subtract off the sum of the mass of the helium and the mass of the uranium. And we get 0.005631 units, or atomic units. The atomic unit is the mass of the proton, essentially. So then you multiply that out by c squared. Now we use a different version of c squared when we're using atomic units. C squared is 931.5 mega electron volts per c squared. So that's your c squared right there, right? And then you multiply by c squared to get rid of the c squared, and that's your conversion. In this case, you get 5.25 mega electron volts of energy. That's a lot. That's a lot of energy that thing's kicked out with. So, beta decay, the same idea, except it's an electron coming out. Gamma decay. In gamma decay, you just get light out, so you don't necessarily get a mass defect out with gamma decay, but you do get energy out in the form of a radiation. Now, you do get mass defect, but it's not like you can measure it's not like you can take the sum of the things at the end and subtract from the original. You have to take this, it's the same atom, it hasn't changed. So you have to know the mass of the different isotopes. And they don't do that for us here, they don't confuse us with that, so we don't use it. But it will be, the mass defect energy will be equal to the energy of the photon that's released, of the particular gamma ray that's released, so we could calculate it. Now we talk about half-life. So here is a graph of how radiation dies off over time. You radiate something is radioactive, and you measure how much radiation is coming off of it to start. And as you keep measuring it in increments of time, eventually, it starts off really high, but it drops off pretty quickly, and eventually it dies out. And this follows a mathematical formula. Now, I think that we're going to do an experiment today with this. I think we should. Anyway, this is the formula for that. So for the decay of nuclear radiation, the number of decays that you have at any particular time after you've started measuring it is equal to the number that you started with. That's the number at time 0 and 0. That's the number of decays, or that's the amount of radiation you're measuring when you first start measuring it, times E, which is the natural number, 2.7 whatever it is, 2.71828 right there, and raised to the negative lambda times T. Now lambda is what we call the decay constant of that particular material. So it depends on the material. And then the T, of course, is the time that has passed. The decay constant is determined by this formula right here. The log of 2, so the log of 2, the natural log of 2 is 0.693, so it's just a constant, divided by the half-life of the material. The half-life is the time that it takes for the material to go from a certain radioactivity, certain amount of radioactive counts, to half that number of counts. So you start with 50 and go to 25, measure the time it takes to do that, that's your half-life for that material. And the half-lives are well measured for radioactive materials. There's tables on them everywhere. So, radioactive dating, or carbon dating as it's often called, carbon-14 dating, uses this to its advantage to calculate how old things are. Let's explain how this works. So here is the carbon-14 cycle. It starts off up here in the sky. We have carbon. Well, no, let's actually start it on the ground. So it starts here in these in plants. Plants breathe in carbon dioxide all the time. That's what they breathe. That's what they need to grow. Okay, it's carbon. The carbon actually, when plants breathe in carbon, that's what gives them everything that they need to become what they become. They need some hydrogen as well, so they also drink water. So you have to have water and carbon dioxide for a plant to grow. You don't even need soil, really. Soil is, it's a good thing because it provides a couple of other really small nutrients that it needs. It needs some phosphorus, needs some iron, some other things. But they don't need much of that. So that can be provided in other ways as well. So in reality, you can grow almost any plant with just water and carbon dioxide. And that's all you need. Nitrogen's a good thing too, actually. But, what's really needed is that carbon dioxide. When carbon dioxide is kicking around up here in the atmosphere, it's kicking around with mostly nitrogen. The atmosphere is almost all nitrogen. It's like 80% nitrogen, 5% oxygen, or 12% oxygen, 15% oxygen, I don't know. 15% oxygen or something like that. And then just like 1% carbon dioxide or less. So it's just very little carbon dioxide in the atmosphere. So you have just a little bit of carbon dioxide, but lots of nitrogen. And as the sun comes up, it sends all these high energy radiation particles down the air. Some of them are neutrons. As neutrons run into nitrogen from the sun, what often happens is it creates a carbon-14 atom. Okay? So how does that work? You have nitrogen, here's nitrogen, high energy neutron, where's nitrogen? Here's nitrogen. High energy neutron comes in here, what happens to it? It actually kicks out a proton, is what it does. Sometimes nitrogen will absorb the neutron and become oxygen like we saw. But sometimes that high energy neutron is so much high energy, it comes in and it pops out a proton and replaces the proton with a neutron. So the nitrogen, instead of becoming carbon, so instead of becoming oxygen, actually becomes carbon. But it becomes carbon-14. It has an extra neutron in it. And carbon-14 is actually radioactive. It's not very stable. It decays with a half-life of about 6,000 years. So it will last for 6,000 years, but after 6,000 years, half of it will be gone. But this process is happening all the time in the atmosphere. Neutrons are always coming down from the sun. They're always bombarding nitrogen, making carbon-14. So any plant that is alive is absorbing a certain percentage of carbon-14. Most of the carbon dioxide that these plants are breathing in is just regular carbon dioxide, but some of it is made with carbon-14, and it's a particular percentage all the time. That percentage stays pretty constant. It's up and down a little bit, but it's pretty constant. As soon as a plant dies, it stops bringing that in. When do plants die? When the stuff eats it, or when they're cut down to make things with, make paper with, or buildings with. As soon as they die, they stop bringing that in. And what happens to the carbon count in them when they die? Well, it starts off with this certain amount of carbon that is the same for every plant, pretty much, and then it starts to die off. Now, if you know exactly how much carbon it should have when it died, and you know how much it has now, you can tell how old it is by looking at this chart, it seems, or by doing the math. That's carbon dating. Now, it's the same thing for animals. Animals are always eating plants. And when they eat the plants, they kill the plant. But animals are eating them every day, all day long, all the time. We're eating something that was killed not too long ago. You know, just maybe days, maybe weeks, maybe even months, but it wasn't that long ago compared to 6,000 years. So anything that you eat has a certain amount of carbon-14 in it. You eat a bag of potato chips, has a certain amount of carbon-14 in it from the potato plant. That carbon-14 goes into your body and makes things like your DNA and your muscles and everything else. But if you die, you stop eating those potato chips and you stop getting new carbon-14 into your body. And then that carbon-14 starts to go away in your body as it decays into something else. And so somebody comes along and measures how much carbon-14 is in your dead body 10,000 years from now. And 10,000 years from now, your body will have lost half of that carbon-14 plus another half, another quarter in the 4,000 years after that. And they'll be able to tell that you've been dead for 10,000 years because they can measure the amount of carbon left in your bones because it is decayed. And that's exactly what they do with that. So here is the Shroud of Turin, which people often believe is an image taken from a early representation of Jesus Christ. So from much earlier than we can have it. So they first found it in the 14th century, but it was carbon dated recently, and in the Shroud of Turin, they found that it's 92% of the carbon-14 that is normally in living tissue. So how old does that make it? Well, to do it, you have to rearrange the equation. You rearrange the equation so that you have the number that you count over the original number, that's your percentage. So you get n over n0 equals 0.92, so this equation ends up being 0.92 equals the e to the negative gamma t. The gamma for this is going to be 0.693, which is the constant over the time constant of carbon-14, and the half-life of carbon-14 is 6,000-ish years, 5,730 years, so they put that in there. So once they plugged all this in, then they can solve for t. How do you solve for t? This is the equation you get. The equation you get is 0.92 equals e to the negative gamma t, where gamma equals this thing here. Well, the way that you solve it is you take the natural log of both sides, the natural log of 0.92, and the natural log of the exponent function is just whatever is in the exponent, lambda t. So then you solve for t and you get the 0.0834 over lambda for t. And then you plug in your lambda and you get 690 years. So at about 1300. So is it likely that it's a direct image of Christ? Well, no, because it's well known that Christ lived 2,000 years ago, or ish, you know. So 1,300 years ago, or I mean 600 years ago is not anywhere close to that. The best it could be is an image of an image, right? That's the best it could be. So, anyway, that is carbon dating. We do the same thing in medicine using radioactive isotopes that usually have much shorter half-lives to measure things that go on in the body, to measure blood. They'll put isotopes into the blood and watch it decay, and as it decays they can make images of things in the body. They use radioactive isotopes to kill things in your body, cancer. So they'll create a radioactive isotope that's only active for maybe a few days, maybe a few months, maybe a few weeks, but it's radioactive enough that it will kill things around it. And they put these little radioactive seeds inside of tumors. And it's only radioactive enough to provide radiation to kill the tumor, and then its radiation dies off over time at that curve. And then you don't even have to remove the seed. It just can stay in there and it can reabsorb in the body. It actually just dissolves. So that's a very common use of radioactive isotopes, created by just putting materials into nuclear reactors. We've talked about the binding energy, but here's a chart of the binding energy. So each atom has a certain amount of binding energy in it. Here we have hydrogen 2, which is deuterium, has this binding energy at how much energy it requires to hold it together. Not very much. Helium 3 tritium requires more, lithium much more. And you get up here into these very, very stable things, have a lot of binding energy in them. Holding them together good and tight. And a little bit less as you get out here towards the unstable stuff. So this is the happy region. This is the not so happy region that gets more radioactive up here. Ugh. Woo! Head rush. Oh yeah. Whew. Okay. Here they're talking about a phenomenon of atomic physics called tunneling. So you can think of particles that are inside the nucleus as being inside of like a well or a bowl, where the walls of the well or the walls of the bowl are the energy, is the binding energy that's holding the atom together. And there are certain situations in where you can lower the boundaries, lower the edges of that bowl, or lower the binding energy. Lots of different ways you can do this. But in these situations, you could think of the particles in here as kind of rolling around in the bowl, but they never have enough energy to pop out of the bowl, to jump out of the side. But there are certain situations in which they can actually tunnel through the bowl. They actually can jump through it. And this has to do with the matter wave, or the matter wave of the proton. The proton, for example, if you cool down an atom, very, very cold, the wavelengths get longer because the atoms are moving slower. And as those wavelengths get longer, they actually can extend outside the physical size of the atom that the protons are in. If their wavelength, if their matter wave is outside the size of the proton, is bigger than the proton, then that proton can exist either inside the atom or outside the atom. And so if they do all of a sudden jump to outside the atom and exist outside the atom, that's called tunneling. And then they can be free to escape, and the atom actually decays and becomes something else. And this is something that happens and it's a quantum effect. It's only an effect. It only happens because of these matter waves in quantum theory. But you can actually take advantage of this to do imaging, and that's what the scanning tunneling microscope does, electron microscope does. It actually creates these situations where electrons can tunnel through materials and tunnel out of materials. And as they do that, they create images. They can be detected where this happens. And you can create very, very high definition images. And you can even detect individual atoms actually with a scanning tunneling electron microscope in certain situations. So very interesting stuff here about that. We won't go into great details about that, but it's an interesting atomic physics thing. And next time we'll talk more about applications of nuclear physics. We're going to try to, we've got medical applications, particles, and frontiers. So we've got time to finish up all three of these when we get back next week. Let's see what kind of homework questions we can do in this section. Oh, thank you.
You're welcome.
What's this for?
We're doing group projects, community service projects for human relations.
Ah,
So,
well, thank you.
you're welcome. Have a great day.
Apparently, I deserve to be happy.
Oh, dude, what the heck?
That class.
I messed up. I didn't get
Do you guys like Hershey's?
Oh, my arms are dead.
It's very kind of them, but I really have a hard time eating.
Lactose intolerant?
No, I just don't like cheap chocolate.
Oh,
I like expensive chocolate.
like Ferrero's?
Oh, yeah.
Ferrero's pretty good, but
Ferrero's is bomb.
Ferrero makes some interesting chocolates, and of course, my wife discovered what's the chocolate sauce that they make. Ferrero makes it's kind of like in a peanut butter jar. What's that stuff called?
Nutella?
Nutella. Ferrero makes Nutella. That's the same company. And Ferrero's specialty is mixing chocolate with hazelnuts, which is good. I love hazelnuts. I love all kinds of like almonds and everything else. But if I'm really going to spend money on chocolate and actually eat just pure chocolate, it's going to be probably from Richard. Richard makes a chocolate. They're out of Paris, and they make chocolate that's phenomenal. Richard, yeah. They're about $50 an ounce.
Yeah.
How, have you ever tasted the stuff that says like 80%?
Oh yeah, Richard makes that stuff. It's good.
No,
I love dark
tried
chocolate.
the 95% one.
95% is not pleasant. 80 I
That
can
was
do.
so strong. I couldn't.
90% is just not pleasant because there's not a way to block the bitter taste. Yeah, you can take out most of the it's kind of like the tannins in grapes. It's little particles that make it bitter. But once you get to 95%, the bitterness just doesn't. It's not manageable. But Richard makes chocolates that are like artwork. Like I'll show you. These are their funky little kid ones for Easter time. But let's go to, what's that?
Weren't they like $50?
So here's a box right here, 68. This one's 26. There's a good price. This box right here is this big. It has less chocolate than that chocolate bar does. Easily less chocolate for $26. And the shipping will be about $20 too, because they have to ship it overnight. But each one of these chocolates is so unique,
So far.
and their flavors are incredible. Then they come with a card that's made of 73% cacao. This card is made of chocolate with gold leaf writing on it. So
I wonder if they get a lot of business around Valentine's Day.
they do. They're a very successful business company. Let's see the flavors.
That's why I never really, I don't know if I can get along very well with the chef because I'm not picky at all.
Here's right here, floral flavors. So let's zoom in here. How do I zoom in? So they have elder tree flower, damask rose, lavender, orange blossom. But then they have stuff like salted butter caramel coulis, roasted walnut praline, sesame praline, pineapple airy ganache, cardamom. That's a good one. Cardamom is an Indian spice from India.
There's a spice that costs more than gold. I just can't remember what it is.
It's called.
I know they do it in India. They raise it elsewhere.
Yeah, I have some of it in my house actually. It's called saffron.
Saffron, yeah.
I have 0.04 ounces or 0.0. I have like 0.1 grams or something like that in my house.
It's more
It cost me
expensive.
$25.
They say it's more expensive than gold.
The really good stuff is, yeah. If you buy there's really expensive saffron out there, and it's not the only one that's more expensive than gold. There's lots of them out there that are, but it's one of the most expensive ones that you can buy anywhere. Saffron is good though. It's a nice. It's kind of a bitter. Most of the bitter ones are expensive. Anyway, yeah, these ones, and these are designed to be eaten in succession. So you start with this upper left one and you go across the box this way, and you're supposed to eat them in order. Yeah, because each flavor builds on the flavor before it. They're designed specifically to do that. So it's kind of like an experience rather than, and it's nothing like you've ever had. It'll taste so different. Like it doesn't, you can't taste the sweetness of it because it's, you know how you taste a chocolate bar and it's kind of got that sweetness in your tongue and your throat that sits there for a while. This is nothing like that. It's, you taste it and then it's mostly in your nose and then it's gone. It goes away. It's incredible. And then you just want to do it again. It's worth it. I've spent hundreds of dollars at this place over the years. They have different varieties.
No shame.
What's that?
Like, I spent hundreds of dollars in
It's worth it.
this place before, and you're like, no shame.
Nope. If you really want to get crazy with this, you go to the. They have a chocolate vault that costs $800, where it has all of their truffles in it. But it's in a wooden case like this big, and the case is essentially air conditioned. So it actually has a little air conditioner in it that keeps the chocolate at just the right temperature and just the right humidity. Yep. Costs $500 just for the case, and then all the chocolates in it cost $300. One of each, and these chocolates are only about the size of your, this finger, the tip of your, this finger or the tip of your pinky. They're tiny little chocolates.
Yeah, they take that stuff seriously.
Oh yes, they're the best chocolate company in the world. One of the best. There's only maybe 10 chocolate companies in the world that are as good as they are. So
Seems they wouldn't happen to have like a partnership kind of deal, like some kind of spectacular 5-star restaurant in France. Would they? 'Cause that seems like a good thing that would go along with expenses.
there it is. Here's your chocolate belt. $850.
No.
See, it's got the humidity and temperature things right there. Pretty impressive stuff. And they're sold out. I mean, they actually sell these things. They sell them to the point that they can't even keep them in stock.
Who owns it? Bob?
No, people with more money than sense, like me. I don't have a lot of money, but I really don't have any sense. So anyway, let's take a look at our homework here. Username. Where's my username? That's close enough. So if you guys know anybody who needs to take physics over the summer, I'm using my new homework system over the summer that's free. I'm excited. It's actually a really nice one. Within each homework problem, you'll have a link to videos. You'll have a link to the book. Let's see, videos, book, and a link to contact the instructor right inside each problem. Cool, huh?
That'd be very helpful.
Yeah.
Videos especially.
You just push a button, and it takes you right to me, or right to the book, or right to the video. I'm excited about it.
Yeah, I don't know about the one we're using right now.
This one is too cumbersome, and it doesn't have anything that they promised. They say that you're going to get all kinds of feedback from live TAs, and I'm like, that's not true.
I only get feedback when I'm like one factor off.
Yeah, it gives you lame feedback. I think that Sapling was better. Would you agree Sapling was better? Sapling had feedback that was easy to understand and really helped, I thought. But still, I don't like. But still, Sapling was very cumbersome to me. It was just a pain to work with. This other program is easy to work with. It's super fast. It's really stable. It's just simple. In fact, I can show it to you. This is the one I want to use. And I use this one for my math classes all the time. And they just started it with, so you've used this with when you did trig with me, right?
Yeah, that's right. Yeah, I did like this one.
Yeah, this one is simple. And so what you see as a student, let's see if I can get here. Let's see, let's go to, so as a student, this is what you see when you come in here. So you have messages, forums, your calendar, the course map, your grade book on the left side, and log in, log out. And then it just starts here. Here's course information. Here's all the weeks of the course, right? Week 1, week 2, exam 1. Week 3, week 4, week 5, exam 2. Week 6, week 7, exam 3, and so on. Just a very simple thing. And then you go to here to week 1. This is where it gets a little bit too much for me because there's just a lot of junk here that they put in that I wouldn't have put in. But besides that, you have section 1, you have a link to the textbook, you have some videos that you can watch, and then your assignment. So you go to your assignment, and this is the assignment. It just comes up super quick. It shows you one problem at a time. You don't have to scroll, which I really hate. You can go to the second question or the 8th question, and it just shows you each question. And then down here, you can get help from a video, or I'm going to be putting in links for the books. I haven't done it yet here. And then a link to the instructor. So you have the link to the instructor when you want to message the instructor. It sends a message directly to the instructor, and you can use math and graphs in your message. You can actually insert pictures and graphs and links to things. So you can insert an actual graphic you can take a picture of your homework assignment. But if you put in here, and you can actually put in math. So I do like this. I do f of x equals parentheses 2 minus x, and then I put divided by 4x or something like that, and then it actually shows it in math form, like that. So that's beautiful. Because then I can show you step by step in math notation, not some funky thing, you know. As long as I do it right, I didn't do it right here. But anyway, the point being is that you've got all these tools that you can use when you're communicating back and forth with your instructor and with other students, because you can communicate back and forth with students using the same system. So you can have students in different places sharing ideas and everything else. But I love this system. It's super fast, super reliable. The calendar is nice because you go to the calendar and you can click on the homework. It tells you what they are, and then you can actually click on the actual homework. It'll take you to that homework assignment. So there's links to everything everywhere. You don't have to go back to a particular place. Lots of different ways you can enter in things. Lots of different ways you can graph and draw things in there. So it's not just multiple choice or enter a number. You can actually graph things and have other things like that. So it's a great system. I love it.
Yeah, I like
Let's do this one. So here, let's see if we can find one that, here's some graphing ones where they actually show you pictures, but then there's some where you can do the graphs yourself or do drawings yourself. It's a great program. And I'm doing it for physics now. I'm starting a physics class in here. It's not been made available to students yet, but if you go here to my first assignment, I haven't made the different things for the stuff in here yet, but lots of different things you can do here. Just started this one. Let's go to this one. So here I've got click to video. It'll take you to a video on that particular subject, or you can read it in the book. It'll take you directly to the book. It'll take you right to the spot in the book that you need. So that's another great thing about it. So anyway, I really like it. All right, back to this obnoxious one. So this is going to be chapter 31. I have to put a description in, which is nuclear physics. Nuclear physics, we'll make the due date. What's today, the 19th? Make it like Monday. Make it like Tuesday. And the same time, that's good. Okay. Chapter 31. Let's see what we got here. Ionizing in a Geiger tube. Yeah, those aren't all that interesting. Suppose we should give you one of them. Not that exciting though. Cube of water. It's done too. Okay, new solar space road, Cassini, radius, spell, nitrogen. This one's good. See you later, Darius. Yeah. Let's do some carbon dating. This is cool stuff. There's another type of radiation. There's another thing that I didn't talk about, the becquerel. That's just a unit of radiation. It's a number of counts per something, I don't remember. But becquerels are they're defined in the book. It's not that hard to figure out.
Becquerel.
Yeah, a becquerel. It's just a unit of measure, like meters. So it's not too hard to understand. We'll do it. We'll take a look at it after we're done here. Deuterium. Binding energies. Oh, you forgot that today's Wednesday. I forgot too. Charge power field and bubble chamber.
Guys, Dave, 30 minutes.
Here they talk about a bubble chamber, but they didn't talk about it in the class. Okay. Not very much to do this. Main problems. Save and exit. So that homework is up and ready to go. The becquerel. Let's talk about the becquerel. The Q. Search. I didn't do anything. Becquerel. Is it searching? All right, let's go back to just finding it this way. Becquerel will be here probably. No, probably here. Maybe not. I don't know where it's going to be. Nuclear radioactive, maybe it's at the very beginning. I don't know. Yeah, probably here somewhere. Nope. Nope. Not gonna be there. Probably here, I guess. So here in this section, we're talking about counts. Every count is a nuclear event or a radiation event. Something comes out and you detect it. That's a count. And the number of counts determines the activity of a substance. More counts, more activity. This activity is given a name called. It's given a unit. The name of the unit is the becquerel, and 1 becquerel is 1 decay per second. So if you're seeing one event, one radiation thing coming out every second, then you have 1 becquerel of activity. The problem is a lot of things have a lot of becquerels of activity. And so we use often the Curie, which is actually 3.7 times 10 to the 10 becquerels. So we use that unit as well for activity. So we have two units of activity, the becquerel, 1 decay per second, or 3.7 times 10 to the 10 decays per second, which is the becquerel. Which is the Curie. So either one of those you can use. When you have fewer decays, you usually use the becquerel. When you have a lot of decays, you use the Curie. And then you can go from there. So anyway, that is that. And moving on from there, we're pretty much done with this chapter. We're going to move on to more of it next time as we look at how we use this stuff in medical applications in particular. Kind of interesting stuff. Next week we might take, on Wednesday, we might go down to the hospital and take a little tour to see some of the stuff they use down there. It's kind of cool. We need to make some plans to do that. But besides that, we're done. Homework's up and ready to go. Tomorrow morning, 7 o'clock here.
Would we take like a,
Yeah, bring me your quiz.
oh,
Or you can leave it back there, that's fine.
would we take like a campus vehicle?
Yeah. So,
When we look at our grades on expert TA, is that just counting homework, or is that?
yeah, expert TA grade is just your homework grade. If you've been here for all of the labs, then you can essentially use your expert TA grade as a good kind of roundabout figure. If you haven't been here for all the labs, then that can change quite a bit.
And can we still bring our labs in?
Yeah, if you get them done, bring them in for sure.
Cause I think I've kept them in my bag, and I keep forgetting to turn them in.
Yeah.
I
I don't even know what does the grade look like in here. Can I even look at it here? View grades. I'm gonna turn this off before I do this. I've looked at them before, but only for individual assignments. I haven't looked at overall grades. Oh, so it's got an average at the end. But does that really tell you anything? Wait, there was an intro to expert TA homework assignment? That one doesn't count. Well, I don't know. Maybe I will count it. Yeah, before you go, if you do have any things that you want to make up, like homework assignments or labs or anything like that, you need to tell me within probably the next week, so that we can arrange that, so that I can open up things, so that you can come in and do labs. We need to arrange some times to make up labs for some people. So if you need to do any of that, please tell me. The only thing that I don't allow makeups on are exams. I'll allow you to come in and I'll allow you to do homeworks again. Just send me an email. But send it before next class, which will be next Tuesday, so that I can make those things happen.
Okay. Will we be able to find out what labs are missing? Will we be able to-
I will go through all the labs that I have and make a list in the next week as well.
Okay. 'Cause I think that's fine.
Yeah. Send me an email for homework in the next by next Tuesday, and I will try to get a count on all the labs by next Tuesday as well. I was hoping that my student who is taking this distance learning would keep up with us, but he's really behind us, and he's probably not. He's probably going to have to make some arrangements to take this class again. But that's one of the reasons I haven't graded any labs, because I was hoping to get his labs and grade them together, so we get a kind of together kind of grading.
Is he emailing you about any problems or anything?
Yeah, he's sent me some stuff in, but he's been behind quite a bit. So, but I'll deal with him with that later. But I will get that done here in the next week as well, so that by next week you kind of know what needs to be done to finish up for the final 3 weeks of class. We'll get it all cranked out for you guys. But send me an email.
We have one more exam, don't
The final is all we have. Yep.
Thank you.
Yep.
May I have your attention, please? May I have your attention, please? A tornado warning has been issued for this area. A tornado warning has been issued for this area. Please take all appropriate safety actions at this time. May I have your attention, please? May I have your attention, please? A tornado warning has been issued for this area. A tornado warning has been issued for this area. Please take all appropriate safety actions at this time. May I have your attention, please? May I have your attention, please? A tornado warning has been issued for this area. A tornado warning has been issued for this area. Please take all appropriate safety actions at this time. May I have your attention, please? May I have your attention, please? A tornado warning has been issued for this area. A tornado warning has been issued for this area. Please take all appropriate safety actions at this time. May I have your attention, please? May I have your attention, please? A tornado warning has been issued for this area. A tornado warning has been issued for this area. Please take all appropriate safety actions at this time. May I have your attention, please? May I have your attention, please? A tornado warning has been issued for this area. A tornado warning has been issued for this area. Please take all appropriate safety actions at this time. May I have your attention, please? May I have your attention, please? A tornado warning has been issued for this area. A tornado warning has been issued for this area. Please take all appropriate safety actions at this time.
You like Hershey's chocolate? Have chocolate. You deserve to be happy. Oh man. Tired, tired, tired. Oh, I forgot to stop my last recording.